So in this unit, we're going to be looking at work and energy. And I'll give you a little outline of the topics we're going to look at. First of all, we're going to look at something called conservation principles, which we're going to get into first. We're going to look at systems and energy. We're going to look also at forces and potential energy. Also look at conservation of energy, and finally getting into power. And when you get into the notes, okay, you'll notice that there are little links that you can scan if you need to get more information. Okay, so some of the most powerful concepts that we learn here in science are called conservation principles. These principles allow us to solve problems without worrying too much about the details. So unlike math, it's not like an exact it's not exact in your calculation. So, for instance, there are a lot of forces acting on every single object in the universe. We don't have to necessarily look at all the forces acting on an object. So if you think of a bag of candy, like Skittles or something like that, if we know there are 50 pieces of candy at the beginning, and then if you take the pieces out and spread them around and then put them back in the bag, you know that there's going to be 50 at the end. So that's just a conservation principle. We know that what's equal in the beginning is equal in the end. So how can we look at that in terms of physics? So I'll give you an example. What we know is that the moon exerts a gravitational force on the Earth. So it must exert a force on every object on the Earth too. So why, when you work out the motion of a drop ball near the surface of the Earth, do we not take into account the effect of moon's gravity? Think about it. If you drop something on the surface of the Earth, like a ball, the moon's actually pulling it up. So why don't we include that in our calculations? Or why don't we include all the other planets that are pulling on that ball that we're dropping? So we need to say that we take the system, okay, I'll draw a picture here, and we box it off. So we're looking at just a system. So we're looking at the Earthball system. Okay, so let me draw a picture of that for you. So let's just call this, and if you take this down in the notes, it will help later to understand. So let's say that I call this an object, and I call this the direction at which it's acting, the forces are acting on it. In fact, I don't even need to put a little arrow. We can just call it that. Okay, so let's call this box the universe. Okay, this is everything inside the universe. And let's just boil it down to a few different things. So we got this, that's an object. That's an object. And notice there's a lot of different directions acting here, and many different objects. So I'll just draw in a couple more here. And there's another one. Okay, and I'm going to put these two here, and then we'll do another one here. Okay, so if this box is the universe, the entire universe, and let's say these are all the objects in the universe. Well, I want to focus or zoom in on just, let's say, 2 of the objects, and we're going to ignore everything else. So if I do that, okay, I can take and divide the universe into the things that I want to actually measure. So if I want to just measure these 2 objects and their interactions, okay, I can do that. I can take everything that I want to look at and put it in this tiny box here. All right, and now we're looking at these 2 objects. This object might be the moon, this object might be the sun, this object might be the moon, this object might be the earth, this object might be a baseball, this object might be the moon. So we don't know exactly what the objects are yet, but we know that we can isolate those 2 objects that we're looking at. And it basically, I know it doesn't make too much sense, but we can ignore everything else. So all of these other objects in the universe, we can take and ignore them. Okay, we don't need to worry about them so much, because they have an effect on these objects, but it's so small, it's so negligible. I don't walk around feeling the gravitational pull of Jupiter on my body. There is one, but I don't walk around feeling that. They're very, very small effects. So we can, in physics, take and just isolate the things we want to look at. So what I'll call this, I'm going to call this the system. Okay, this is our system. And then we'll call this the environment. Okay, so inside the box is the system. You're going to hear me refer to that a lot. And this is the environment. We're going to ignore the environment and focus on the system. All right, so we're going to ignore this, so the rest of this stuff, and focus on just the system. So furthermore, we can actually call this system that's boxed in, we can either call it open or closed. We're going to be working with a lot of closed systems, okay, which means we're just looking at these two objects. When you're looking at an open system, then you're going to take this and include all these other objects in there. So when we get into electrostatics, we'll be looking a little bit of we're going to be looking at open systems more because there's a lot of other factors. But for the time being, we're just looking at a bunch of closed systems. So here we go with the energy. If I have a title here, I'll call it energy change in systems. Okay, so what we're going to look at is the fact that energy in equals energy out. Okay, and I'll give you a typical example in this system. So in this system, we say that energy, and I'm going to boil this down, energy is conserved. Okay, when I think of the word conserved, I think of a couple words come to mind: saved, reusable, that type of deal. So what I'll give you an example of is a car. Okay, so let's say here's my car. Okay, and here's the fuel tank. Okay, here's a fuel tank. And I pump fuel into the car. Now, the thing about fuel is that it contains energy. Okay, so let's just say, for ease of calculations, let's say I put 2 units of energy into the car in terms of gasoline. And then the car gives me something in return. So like if I put 2 units of energy into the car is going to give me a couple of the things. Okay, first of all, the car is going to give me motion. Okay, that's the whole point of having a car, right? The car is also going to give me heat. Okay. And also the car is going to be pushing against friction, which will actually be included in motion. So let's say there are 2 things the car gives us back: motion and heat. Okay, if I ever want you to put 2 units of gas in the car, then the motion plus the heat of the car, so if we add these 2 up, motion plus heat, it's got to equal, take a guess, it's got to equal 2. So what I put in, I got to get out. What I put in, I got to get out. So this energy is never, ever lost. It's not lost. Nothing in the universe is lost, which is pretty cool to think about, because if I put 2 units in, I'm getting 2 units out no matter what. Okay, now it just turns out that cars are actually better heaters than vehicles. So they produce more heat than they do motion. But we do get a result of what we want as far as the car moving. So we've got, let's say, motion plus heat is 2. Let's say that 1.2, let's change it a little bit. We'll say 1.2 equals heat, and then 0.8 is motion. Okay, and that's a fraction. So we can find, and we know that when energy is conserved, and it is, energy is not created or destroyed. Okay, this is big. Okay, this is big. Energy is not created or destroyed. Okay, that means that energy just moves. It flows. It's like a system. And we can get into some debates about this, and hopefully get you thinking a little bit, because this word here, created, okay, leads us into some different types of even philosophy. Even destroyed, so if things are destroyed, they're not destroyed. You think that they're destroyed, but they're actually just changed. So given the concept that energy is not created or destroyed, okay, we can come up with some formulas for this, because I'm just going to say that energy initial, or energy in, equals energy final. Okay, then we'll call this initial equals final. Okay, so energy initial is energy final. And it turns out there's only 2 ways to change the energy of a system. One of them, with the car that I just gave you, the example is with heat. And the other one is with a system called work. So we're going to focus on work here. So if we look at this equation, and now this is a system where nothing really changes, nothing happens. If we have a piece of uranium here and we just let it sit there for an hour, it's still going to be just a piece of uranium. But if we add something to it, so let's say I take this, energy in plus the work that it produces is equal to the energy final. Okay, so this work is going to be work. This is a system of energy. So work is energy. Okay, work is energy, and this can be defined as something that is moving. Let's say moving energy. Okay, and it turns out that work equals a force, which we've learned already what forces are, multiplied by the distance the object actually moves. So this is force multiplied by distance. Okay, so when we do work to an object, we're moving it a distance. Okay, it'd be important to take this one down in the notebooks. So let's get into what work actually is, and we'll look at some units, and we'll talk a little bit about how we do a couple of calculations with work and energy. So here we go. So work equals the force times the distance. Okay, so this equation gives us the units of work. We already know that units of force are newtons, the units of distance are meters. So let's just break this down a little bit. So work, the units of work are equal to newtons times meters. Okay, so I could say that the unit of work is a Newton meter. Okay, so rather than call it Newton meter, okay, we're going to call it something else. We're going to call it a joule. So, it's in honor of James Joule, who made the contribution to developing the idea of energy. So this is just the guy's name, but we're going to, instead of a Newton meter, we're going to call it a joule. And we can actually abbreviate joule, J. Okay? So here's where we have our units here. And if you're looking through the notes, you're going to see that there's something called negative work and positive work. Okay, don't get too hung up on these ideas. They can be confusing. Just realize that to get a negative work, we've got to have either a negative force. So let's look at it. In order for work to be negative, we've got to have a negative force or a negative distance, okay, or displacement. So, don't let this confuse you. It's just a sign thing. Okay, negative work means we have a negative force or a force going in a negative direction, or a distance going in the negative direction. So when we talk about negative and positive in some of the questions, that's just what you're going to look at. Okay, this was a long segment, about 17 minutes. I'm going to stop here. Okay, let you do some of the problems, and we'll move on to gravitational potential energy next.